Good morning. Let's begin. Your rainfall homework assignment is due on Tuesday, and I got a good question from Levi this morning. He's already been working on the IDF curve part of that. He asked, how high are you supposed to go on your IDF curve? And you have to go at least to the 25-year storm. Depending on what site you choose, you may identify a rain gauge that has data back 60 years, and then you could do the 50-year curve. But it needs to at least be the 2, 5, 10, and 25. All right? So that assignment is due on Tuesday. Also on Tuesday, we're going to have our first midterm exam, and the coverage for that is through our first lecture of the semester up until today, including today. And if you look at the course schedule that I provided at the beginning of the semester, and it's also posted on MU Online, it identifies which sections of the book correspond to the lectures that we've had. And it's not all of chapter 15, 16, and 7, but it's portions of those chapters. There are some materials that we either haven't covered yet in the case of chapter 7, or some things that weren't included in 15 and 16. So the full details are on the schedule. There's going to be 2 parts to that exam, a conceptual set of questions that you'll complete first. And during the conceptual questions, you won't have access to any notes. It's just strictly going to be you, your brain, and the pencil. And then on the second part of the exam, it's more oriented towards problem solving. And so it may be questions related to the software. It may be some calculation problems. So those will be about evenly weighted in terms of the point values. About half of the points will be related to conceptual questions. About half of the points will be problem solving. So it's very important that you refer to that list of concepts that I provided you on the first day of class, and you're able to define and explain each of those terms. You can use an equation sheet for the second part of the exam, but it can only include equations. So for example, Hyet is a software program, and I don't want your equation sheet to explain how you should follow every single step in order to do an Hyet analysis. So your equation sheet shouldn't be a tutorial for yourself. The exam is seeking to identify what you've learned already, not what you can fit onto an equation sheet. So I'm going to collect those equation sheets at the end of the exam just so I can make sure all that you had on it was equations and variable definitions and not an outline of how to use software. Yeah?
Do we have, like, for the crest length in Hyet, can we explain what that means?
You can have variable definitions, and so if you want to have L equals and then the phrase that describes that.
That's what I have trouble with, is like knowing which one to put where, like what's given in the problem and where to put it.
What I'd really like you to do is to know that stuff and understand it, and for the equation sheet really to be focused on formulas and defining the variables in those formulas. Yeah. Other questions about the exam? We'll have 75 minutes, and I'm going to write it with the intention that the average student can finish the exam in 60 minutes. And so if you're a little bit slower than average in taking exams, you may take the full 75 minutes. But part of how well you know software is how quickly you're able to use it. If you're given an infinite amount of time, chances are you'd be able to answer any question. But what I'm hoping you can do is show some proficiency in using the software. It was a disaster last time we used the tablets for the quiz last time. Ultimately, actually, the grades were very good. Almost everyone figured out how to do the analysis, and so it took us a long time to get the software running and the computers logged in, but ultimately it worked out okay. I hope that it'll be better next time. I'll certainly make sure that the tablets are charged, but there's nothing I can do about there not being enough login servers available or whatever that error is. I had the IT guy take a look at the tablets on Tuesday afternoon, and he said it's fixed, but he said that before, so who knows. So the take-home message is if you've got your own PC, most likely it's more reliable than these tablets. So, any announcement questions before we continue our discussion about precipitation? Today, last time we focused mostly on how to get precipitation data because you needed that information to start on the homework. But today what we're going to focus on is the fundamentals of what causes rainfall. And I think the phenomena involved are really interesting. So just as a review, these three different websites that I briefly identified in our last class period, the first one, Prism, what it does is it interpolates data from all of the rain gauges in the United States. You know, rain is measured at a single point with a gauge like this, where we only know what the rainfall is in the area immediately above this rain gauge. So if it's raining right here a certain amount, there's no guarantee that over here it's raining the same amount. And I'll show you some gauge data today of the difference between rainfall in Huntington and Ona, which the two gauges are less than 20 miles apart, but there are some distinct differences in what the precipitation patterns look like, even just 20 miles apart. So what Prism website does is it interpolates using a computerized program, and it provides the rainfall in 2 kilometer by 2 kilometer blocks through the entire United States. You're not actually going to need to know it for any homework problems that you've got, but I've used it in research before, and it's actually a really interesting tool just to look at the images they put together, even if you're not interested in the background data. Now this precipitation frequency data server is where you can get the IDF curve for any place in the US. And so this will tell you the design storm for a 2-year storm, a 5-year storm, a 10-year storm. And it presents that data both as a table and as a figure. And so on the homework, you have to go to this website to get the table data that then later on you're going to graph. And finally, the NCDC, that's where you can get the individual data for a specific rain gauge. And that's the website you need to use to download the precipitation data for a certain gauge so that you can make your own IDF curve from that. How long did it take you to get your rain data, by the way, when you set in your request?
Well, actually, I had to do it twice.
Mm-hmm.
The first time I did it for a city,
Yeah.
a bunch of stations.
Oh.
But I didn't get the email the first time. I got the submittance email, but not that I got.
Yeah.
So I had to go to the submittance email to check status.
Checked status and it was ready?
Yeah, but
They never emailed you that it was ready? That's strange, because I always get the it's ready email, but sometimes it is ready before they send me that message. Maybe you'll get it in a couple days. 2 minutes?
yeah, the second time I got an email that was ready and it was like instant.
Okay. You must have not been working during the peak period when everybody wants to know rainfall data. There must be some sort of like a rush hour on getting rain data when it took me 8 hours that one time. Okay, so here is a rain gauge that is really interesting because I'm going to actually pass it around. Please don't drop it. I just got it this morning. It literally just came out of the mail, and it's perfect timing. But the rain falls in a certain area and goes through a funnel. It'll just drip into these containers that each one of the tips, every time it tips in here, there's a data logger that can sense that tip. It's just basically some flash memory, a little battery, and a processor, and it can tell every time it tips, and it records what time it is. And the amount of rain it takes for this to tip is 1/100th of an inch. And so that's the volume of the little cup in there. And so when there's just the right amount of water, the balance causes it to tip over. It drains out of the bottom. Here's the drain. And then the empty cup is ready to start receiving more water. And so it allows you to know the rainfall with a lot better resolution than just every 24 hours. You know, the alternative to this is taking a ruler to a bucket and measuring how much water there is in that bucket. But then the problem with the ruler and a bucket approach is, what if in between your measurements there was some evaporation too? So this never sleeps. It's going to take rainfall data at 3 a.m., 4 a.m., and so as often as it's tipping, that's how much resolution I've got on the data. So let me just pack the data logger back in here, and then I'll pass it around for you to take a look at. I've got one of these set up at a small watershed east of here, and it's been recording data for the last 3 months, and it's a really great system. I mean, that only cost $400, and that seems like a lot of money, but it's just spectacularly cheap compared to some of the other methods that have been used till now. When you are recording rainfall, the rule of thumb estimates, the rule of thumb guidelines that are given for measuring rainfall is that the opening shouldn't be less than 30 millimeters because, you know, the raindrop could actually be split in the middle, and so you want, just for purposes of sampling, the opening to be at least 30 millimeters. Obviously, if it's not level, then if it's tilted, then it's not going to intercept the correct amount of rainfall. And then also, there have to be some corrections for its capacity to shield for wind and how high off the ground it is. And so this can show, this figure that's up on the screen now shows wind shielding effects. There can actually be a little bit of turbulence over the front face of that. So a sideways wind could deflect some of the rainfall that it's supposed to accept. And that's part of the reason why they say the orifice should be at least 30 millimeters in diameter, is that you don't want wind shear to be pushing raindrops out of the way. So one of the solutions to that sometimes is that for really sophisticated rain gauges, they'll try and put a bell shape, an inverted bell shape at the top of the gauge. And then there are graphs like this where if you have a certain amount of wind speed that you're measuring, then you can estimate how much of the rainfall was actually intercepted and how much of it maybe was deflected. And so this gauge doesn't correct for how windy it was, but a really sophisticated unit like they have at airports probably does on the fly automatically correct for how windy it is and what percentage of the rainfall was deflected due to turbulence. So here's that data that I was mentioning. Just yesterday I offloaded the data off of the rain gauge that's in place right now in Ona and looked at the rainfall data for the comparable time period for the Huntington Airport. And the Huntington Airport is almost right on the border of West Virginia and Kentucky, so it's a little bit west of here. Ona's a little bit east of here. But you can see that they are some distance apart, and usually when there's a big storm, it will rain a little bit in Huntington, it'll rain a little bit in Ona. But it seems like for some of the time, the rain is in Huntington before it gets to Ona. And that goes back to what we were talking about last time, is the typical pattern of storm movement is from the west towards the east. And so if you look on a rainfall day-by-day basis, the storms typically hit Huntington before they get to Ona. But just because it rains in one location doesn't guarantee it'll rain in another, because there are some instances where the storm is localized. So some other considerations when you're measuring rainfall is that obviously you need to keep the rain gauge away from obstructions like a house or trees, and that's a hard thing to do in a heavily forested area like West Virginia. The place that I've got the rain gauge located is, I don't know, it probably is right at the limit of 45-degree angle away from obstructions. And the reason why you would want to avoid that is that obviously even a tree is going to have some of the rainfall intercepted by the leaves, and the leaves have to get wet before any rain will make its way to the ground underneath the tree. And so you don't want to measure the effect of the rainfall and the tree with a rain gauge. You just want to know when the rain was coming out of the atmosphere and started to hit the canopy. And so that's why it should be in a clear area. Like I said, evaporation losses can be significant if you don't have a tipping bucket like this. This is called a tipping bucket rain gauge, and it doesn't really look like a bucket in there. It's more of just a tiny little cup on a fulcrum. But the way that rainfall totals are averaged, there's several different approaches. And the easiest is just to identify rain gauges in the vicinity of a watershed of interest and just take the average. And they call this an areal average because it assumes that each one of the gauges has an equal importance in identifying the average over the area in question. So in this illustration, we have some watershed boundaries, and this line that's drawn here is like a ridge line. When we were looking at a watershed using Google Earth last time and sort of pivoting around in 3D with the DEM data turned on, we could sense that there are high points in the mountains and in the hills, and so this boundary here is the delineation of high points in the hills, and so all of the water inside of these boundaries is going to be making its way towards an outlet. So we want to know what's the average rainfall inside of this watershed. The aerial approach just says take all of the gauges in the area, whether it's outside but pretty close to the boundary or inside the boundary, and give them an equal weight. So the weakness of this approach, as is obvious, is that we have a huge variation in how much it rained here. This must be a pretty big watershed to have one location where it only rained 0.74 inches and another where it rained 9 inches. And they're really exaggerating the values here just to make a point with the different methods that are shown. But if you just average without taking into account which one is inside the watershed and which one is outside of the watershed, then the Wyatt should be more important than the Emmettville, but in just a simple average, they're given equal weight. Here's a little bit more sophisticated way of doing it. It's called the Theissen method, and with the Theissen method, the approach is to draw a line between two rain gauges. So look at Hang Tree and Upper Falls. Basically, this line is halfway between the two, and if you were going to draw a line connecting the two, it's perpendicular to that line that connects the two. And so you draw a line in between the two, and you do the same thing for every two gauges. Foster and Hang Tree has a line that we could draw, and then those two lines intersect, and you basically are drawing lines all around, and then this area corresponds to what we would say Hang Tree's influences. That rain gauge everywhere that has this boundary is going to be assigned the depth of 2.68 inches. And so Lower Falls, if we drew the line between Big Creek and Lower Falls, you can see Lower Falls, even though it's outside of the watershed boundaries, it's still, that precipitation depth is going to be assigned part of the segment of the watershed that's closest to Lower Falls. So I have a chance for you to try out this Theissen method. Let me hand out this activity here. This is going to count as homework points. We're doing this as an in-class exercise, and you can work together with a partner on this. I'd like you to get a chance applying the Theissen method because sometimes there are computer programs that do this automatically in the background, and we don't necessarily appreciate what it's doing or understand what it's doing until we've attempted to do the same thing manually. Enough. Okay, so you can work on this individually if you prefer, or you can work on it with a partner, but we're going to take about 6 or 7 minutes and go through this process of draw a very faint line between two rain gauges, then put a thick line between them, and do that for all the rain gauges on the page, and try and identify the boundaries, and then I show the depth for each one of these gauges, and you should calculate what's the average precipitation depth for the entire boundary. And I say the formula is, it's the area of each segment multiplied by the depth of that segment, and then you divide by the total area. There's another way of doing this average, and it's called the Isohyetal Method. And instead of identifying which rain gauge is going to be used for which area, in the isohyetal method, what you try to do is make a contour based on the data that's available. And so each one of these lines on the contour refers to a different precipitation depth. And so averaging between 6.9 and 2.68, you can see that they're saying here is the 3-inch line, here's 4 inches, here's 5, here's 6. And so you said it's not all going to be, in the Theissen method, the silly assumption that this makes is that everywhere inside of Upper Falls is 6.9 inches. And then as soon as you go over the border between this area and the next one, instantly the rainfall goes from 6.9 inches to 0.89. And of course that's not realistic, that there's not a magical line in the sky where it's raining really hard on one side of the magical line and really lightly on the other. So the Theissen method is unrealistic in that way. And so the isohyetal method, which is a little bit harder to do by hand, assumes that there are going to be gradual variations in rainfall depth over the area. And so they try and make these contours. And computers can do it really easily. People can't do this method quite as easily, although some folks are really good at, sort of interpolating graphically. And then what you do is the same approach where you find out how much of the area is within the 4 to 5 range. And so you'd calculate the area of that band, and then you'd assign it the average rainfall depth between 4 and 5. And likewise, you'd find how much area is there between 3 inches and 4 inches. You'd count that area, and then you'd multiply it by the average depth between 3 and 4 inches, and so on. So I may not ask you to compute isohyetal method on the exam, for example, but maybe what I'd ask you to do is explain how it works. And so you need to be able to understand what is the calculation process, or what's the theory behind this method. And this method's theory is that there's a gradual change in precipitation depth over an area, and then you'd calculate the area in between boundaries and multiply the average rainfall depth associated with that area. So just because we're not doing calculations doesn't mean that you can forget it. Here's another figure that's illustrating this term spatial distribution. And remember, last time we talked about how spatial distribution is a phrase that's used to describe how some property isn't the same over an entire area. And historically, it's much wetter in the eastern United States than it is in the western United States. And so that is a almost permanent spatial distribution. Here's another illustration of spatial distribution. It's showing the rainfall on Oahu, which is one of the islands of Hawaii. And we're going to talk in more detail on why there's so much of a variation, but if any of you have been to Hawaii, you know that it's very green and tropical on this side of the island, but then on this side of the island, it's almost like a desert, actually. You think of everywhere in Hawaii as a tropical island, but it hardly ever rains over on what's called the leeward side of the island. The annual rainfall is between 500 and 800 millimeters, whereas on this windward side of the island, there may be as much as 5 meters of rain per year. It's an enormous, that variation is really huge. And there's a specific reason for the difference in rainfall patterns. Does anybody know, by the way, why it rains more on this side of the island than on that side? Yeah, but the forest is there because the rain is there. So why is there rain here and not there? It's partly having to do with the wind. The wind blows from this direction towards that direction. That's the typical wind. Now, that doesn't mean it never blows the opposite way, because sometimes, obviously, it will. But most of the time, the wind blows this way. But it's also because this is where the mountains are, on this side of the island. And then it's flat, mostly flat on that side. And the mountains have a very important role to play in precipitation. It's one of the three main ways that it rains is when there's mountains. There are three main phenomena that cause precipitation. We're going to talk about those today. There's another thing called temporal distribution. So we already know what spatial distribution is. Temporal distribution says that not everything is even over time. There may be patterns or variations in how much of something comes at what time. So this temporal distribution in precipitation shows that if we look at Denver, for example, Denver, Colorado, most of the rainfall is in the spring. April and May is when they have lots of rain in Denver. But now compare that to Seattle. In Seattle, it's almost the inverse of that. There's very little precipitation on a relative basis in the spring and summer, but then there's more rainfall in December, January, February. And so temporal distribution says that over time, the precipitation varies. It's not always every single month having the same rainfall totals, except for, it looks like Boston is pretty even on a typical basis. Here's an interesting figure that shows the average number of days that have thunderstorms. So thunderstorms being these really intense rainfall events where a lot of precipitation comes all at once. And if you look, Florida has lots of thunderstorms, portions of Texas, but then along the west coast, there are very few days that have thunderstorms. There is an approach to estimating rainfall that's called the maximum precipitation, and it looks at how much water could possibly come out of the sky at a certain location. You're trying to put an upper limit on physically how much moisture can the air hold and how much of it can come out of the sky at once. And these are all record storms that are on this graph. But what the graph is showing is the duration of the storm and how much rain, the depth of the storm, based on a duration. So Barrow, Guadalupe had a very high intensity. It was 1 minute of rainfall, and it was almost 2 inches. So that's an unbelievable rainfall intensity. It would almost equate to 120 inches per hour if you think about it on an hourly basis. The 100-year storm, just to give you some perspective, in Huntington, the 100-year storm, the most intensity we would expect for the 100-year storm is maybe around like 8 inches per hour. And so here, this was a storm that it didn't last very long, thank goodness, but they really got a lot of rainfall very quickly. And it turns out that if you graph this on a log-log scale, so logarithmic time on the x-axis, logarithmic rainfall depth on the y-axis, then it follows somewhat of a linear trend. So you can estimate what's the probable maximum precipitation for a certain storm length. And historically, it's interesting. Here's a West Virginia's on the map. That corresponds to, looks like the 2-hour storm, Rockport, West Virginia. I don't know anything about where that is or when that storm was, but this is really important, maximum precipitation, when you're doing analysis for dams, because you're not interested in the 5-year storm or the 25-year storm when you're looking at the safety of a dam. The failure of a dam is much more catastrophic than the failure of a culvert. You know, if a culvert is too small, then the water will overtop the roadway. And we don't like that, but it doesn't mean it's the end of the universe if a culvert overtops. Maybe it will cause damage, maybe it won't. But think about if a dam fails, then all the civilization downstream of that dam is threatened. It can really be catastrophic. And so we don't think about even the 100-year or 200-year storm when considering dam safety. Instead, we look at what's the maximum precipitation. Now, what's the theoretical upper limit to how much moisture could possibly come out of the sky, and so then they try and provide that much capacity in a dam so that there's always enough room for additional rainfall if it comes. Here is a statistical representation of probable maximum precipitation for the United States as a function of the drainage area. And it's interesting, I want you to be familiar with the trend. So this direction is increasing storm duration, and then this direction is increasing watershed size. And so the trend is that if you have a small watershed, you can expect a higher rainfall amount than if you have a large watershed size. And these are all depths. This isn't volumes. This is a depth. So why do you think that if you have a 10 square mile watershed, you could expect 24.7 inches as a maximum, a theoretical upper limit, but for like 1,000 square miles, it would be almost half that? Why is it that a small watershed means you can have a higher maximum upper limit? Any guess about that? Takes less time. No, this isn't talking about once it rains. It's actually, although what you say is true, you know, a small watershed, the water moves around in the watershed, but this isn't runoff. This is just the precipitation onto the surface. So we have a small watershed, and we're comparing it to a large watershed. All right? So the issue is thinking about how big is a cloud, you know, and it starts to rain. Maybe this high-intensity rainstorm, all of it unloads on a small watershed, whereas the same rainstorm is only going to be able to rain onto a part of the watershed at any given time. I mean, 1,000 square miles, it's very unlikely that you'd have a storm where it's raining over the entire area all at once. If you look at a weather map, usually you see the weather moving. You know, the storms, if you look at a weather map of the United States, or even just, you know, like West Virginia. Here's the worst drawing of West Virginia you've ever seen, all right? Okay, so when you see a storm, it's usually like a thin band, right? It's not covering the whole state all at once. It's usually just a thin band that's moving across the state. And so if you have a small area, if your watershed is small, maybe this thin band of storm is covering your whole watershed all at once. But if you have 100,000 square miles, it's almost impossible that that whole area will simultaneously be covered by a high-intensity storm. I mean, maybe it'll be covered by clouds, and in some of the part of that watershed it will be raining, but not all. And so that's why the average is so much lower. The letter? I don't know. I think that these are probably footnotes that's referring to specific events that this data is based on, but I'm not certain about that. And then the other trend for duration is obviously the longer the storm lasts, the more the depth will be. So a storm that lasts 72 hours, you're going to end up having more rainfall than a storm that only lasts 6. So again, just to get you thinking about what you need to be able to do for an exam, I may show you this table and say, explain why a small watershed has more rainfall than a large watershed. And you'd need to be able to understand and explain in terms of how much of the watershed could probably be covered by a storm at any given time. Here is a graphical illustration of the very same effect. So this graphical illustration is showing that if you have a small drainage area, most likely the storm is going to be short. And so it's not going to last very long because the clouds will pass over the area very quickly. But if you have a large drainage area, the storm will last longer because it takes a longer time for the clouds to move over the area. And so this on the y-axis here is storm duration. And we'd expect short duration storms on a small watershed. And remember from the IDF curve, a short storm has a higher intensity. A storm that lasts for a long time, the average intensity is going to be lower. This slide is an illustration of how spatial distribution can be estimated. There's an empirical expression that allows you to just sort of interpolate based on the watershed area how big the storm will be relative to some average known amount. And so what the trends that this is illustrating is that a storm that is short, this 30-minute storm, has the greatest deviation from the average, because a short storm, you're going to have a lot of variation. It may only be 60% of the average storm amount in any place, whereas a storm that is lasting a long time, there's going to be more variation in the storm in any one place, and so it's going to be closer to the average. I'd encourage you to read the text, as I always do. Look for this figure in the text and read the explanation that goes along with it, because it'll do a lot to cement these concepts in your mind. Later in the semester, we're going to use a software program for watershed modeling. It's called WMS. And one of the things you're going to do when you're in WMS is you're going to look up the rainfall depth from the Precipitation Frequency Data Server, that website that I showed you. So you'll find how much the rainfall depth is. But then WMS needs to know, well, how much did it rain during the storm? It doesn't want to know only the 24-hour average, but it wants to know specifically on a minute-by-minute basis how much did it rain. Well, this map is showing that in different parts of the U.S., we have different patterns in how it rains. And just to give you the most extreme illustration of that, Zone 1A is referring to the Pacific Northwest. So Zone 1A has Seattle and Portland, north of San Francisco, so the redwoods, the forested Northwest. And 1A is typical of storms that never reach a very high peak intensity. It just sort of is a constant drizzle for storm 1A type. And this graph is showing you during a 24-hour period how much of the rain accumulates at what part of the storm. And if it is just a straight line, then that would mean that the rainfall intensity was constant through the entire 24 hours. And type 1A is the closest to that straight line from edge to edge, where type 1A, it never gets very steep. Here's just a little bit right here, a very brief time in a 1A storm where the slope is pretty high. And remember, a steep slope is going to mean a large intensity. A flat slope, as close as this can get to a flat slope, is going to be indicating constant intensity over the entire 24-hour duration. It's important for you to recognize that this is a graph of slope. And so here is our straight line. Okay. Now, on the other hand, a type 2 storm, now we're in zone 2 for West Virginia. If you look, most of the United States on an area basis is type 2. Type 2 has a very, very long, steep part where most of the rain is happening over the course of just about an hour, maybe 2 hours. If you bring this down, it says that before this really intense part of the storm, it maybe only had accumulated 20%. So during the first 11 hours of the storm, only 20% of the rainfall occurred during the first 11 hours of the storm. But then, from hour 11 until hour 13, so in 2 hours, it goes from 20% all of a sudden all the way it is at 75%. And so there's this deluge. Instead of being an even, steady drizzle like they have in Seattle, here in West Virginia, it rains very slowly, and then it pours, and then it rains lightly again, just a little bit. So there are these typical patterns, and this is another illustration of a spatial distribution and also a temporal distribution, both of them. It's spatially distributed because In different parts of the country, we have different patterns. And then this is a temporal distribution because it tells you during the actual storm, when is it raining most and when is it raining just a little bit. Any questions about these different storm types? So that modeling program, WMS, the computer, what it does is you tell it maybe in a 24-hour period the rainfall was 3.2 inches. And so what WMS will do is it multiplies 3.2 inches by everything on here, and it will tell you how much it rained during each hour of the storm. You know, from hour 0 to 2, you'd multiply the rainfall depth by, well, if we're a type 2 area, you'd multiply it by this, so that at the end of the storm, you're at 100% of the rainfall depth. And before that, it's telling you what fraction of the rainfall depth has occurred up to a certain point. So this is the data table that's sort of behind the temporal distribution. And there's also 6-hour storms where you can compare the behavior of the watershed if you have a short duration storm versus a longer duration storm.
When does the storm begin? First raindrop to the last raindrop? Is that how you measure?
Yeah. And how realistic is it that a storm is going to last exactly 24 hours, like with a stopwatch? Of course, that never occurs. But since that's how we measure rainfall data on a 24-hour cycle, then we apply the measured rainfall 24-hour period to this, and then it tells us on a typical basis how much it's going to rain for the design storm. The actual behavior in real life is going to be different from the design storm, but hopefully the design storm is close enough to the real life behavior that our hydraulic structures are the right size. There are these maps. This is in your book. Hydro 35 is in your book, and the precipitation frequency data server is based on this kind of data, where it looks at over the United States, where are there places that it rains a lot, like Miami, and where are there places where it doesn't rain as much, like North Dakota. And this is showing a 2-year, 60-minute storm. So 2-year return period, 60-minute storm is the duration of the storm. And there are these contour lines that's showing where the rainfall depth during that storm would be 2 inches, 2.2 inches, and so on. So here's the 2-year, 60-minute storm. This next figure is showing the 100-year, 60-minute storm. And so you can actually interpolate all the other year depths from, if you know the 2-year storm and the 100-year storm, you can sort of get an idea of what the rainfall behavior is in between that. This is showing how you can interpolate. If you know the 2-year depth and the 100-year depth, then you can interpolate the 5, 10, 25, and 50. And then likewise, if you know the 5-minute and the 15-minute duration, then you can estimate the 10-minute duration. And if you know the 15 and the 60, you can estimate the 30-minute duration. So you actually don't have to have that much information. You just need the 2 and 100-year to be able to interpolate all the other return periods. And then you only need to know the 5, 15, and 60 to interpolate the 10 and 30-minute durations. One of the most common mistakes that students make in this course is not being able to understand the difference between rainfall depth and rainfall volume. Because the rainfall data that we gather is expressed in terms of a depth. We'll talk about an inch of rainfall, and sometimes that's confusing to someone who's more used to talking about runoff in terms of cubic feet per second. So how do you go from inches per hour into cubic feet per second? And the thing to keep in mind is that whenever it rains, it's not raining onto a point, it's raining over an area. And so that if you know the dimensions of the area, if you know its width and length, then you can calculate that area. And so the rainfall depth that falls over an area turns into a volume. Another concept that sometimes students struggle with is distinguishing a rate with a depth, or the length of rainfall. And so sometimes an IDF curve will be given a rainfall intensity, and sometimes an IDF curve will be expressed in terms of just the rainfall depth that occurred. And let's go to the precipitation data frequency server just to illustrate those two different things, because we can get both from the site. So West Virginia, here's this little red mark, and I'm going to drag the red mark over Huntington. Huntington is in my crosshairs. And now down here, all right, so precipitation depth. Now let's look at this data and see if it makes sense to us. So it says that for a 24-hour storm, a storm that lasts one day, the 5-year storm is going to have 3.21 inches, and the 10-year storm is going to have 3.66 inches. So that makes sense, because we know that the higher the return period, the greater the precipitation depth. Also look at the difference in different rows. So a 5-minute depth for the 5-year storm, it's only 0.5 inches. The 10-minute, 0.7. The longer the storm, the more the depth is going to be, even if the intensity is going down. Because remember, a 24-hour storm is going to be less intense than a 1-hour storm. So this is not a graph of intensity. This is a table that is showing precipitation depths. But now let me toggle that. From instead of looking at depth, now we're going to look at intensity. All right, so it's the same location, the same data, but just expressed as an intensity instead of being expressed as a depth. So now compare the difference between a 24-hour storm and the 1-hour storm. Let me scroll so I can actually point to those a little bit better. All right, so here's the 24-hour, and here is the 1-hour storm. Okay, let's look at the 5-year. A 24-hour storm is going to have an average of intensity of 0.134 inches per hour, but then the 1-hour storm is going to have 1.66 inches per hour. So it's a shorter storm. It has a higher intensity than a storm that lasts a long time, has a lower intensity, but as we saw before, it ends up having a greater amount. So let's switch back to depth again. Depth. So comparing 24-hour to 1-hour, the 24-hour storm has a greater amount. 3.21 is the total depth. Even though it had a lower intensity, it has a longer time. And so the formula to convert between the two is that depth is equal to intensity times time. And so when I'm switching back and forth between the two, it's either showing me the depth or the intensity, and it really only knows one of them, but it's just multiplying by whatever time there is in order to generate the rest of the table. So for example, if it knows the intensity, okay, intensity, let's look at the 5-year 24-hour storm. Okay, so the intensity is what? 5-year 24-hour storm, 0.134, 0.134 inches per hour. And then let's compare that to the 5-year 1-hour storm. The intensity is 1.66 inches per hour. Okay, so what should be the depth? The depth will be 0.134 inches per hour, which is the average over that 24-hour storm, times 24 hours. Can somebody with a calculator tell me what is the product of those two? 3.216 inches over during the 24-hour. Now this one's easy. If it's a 1-hour storm, the intensity of 1.66 inches per hour, the depth is going to be 1.66 inches. Okay? So let's go back now. This was a graph of intensity. Let's go back to depth and just double check. So 5-year, 24-hour storm, 3.21. Good. The depth for the 1-hour storm, 1.66. Good. Yeah?
So is this what you want on part 3 in the homework?
Yeah.
Perfect.
A graph of this data. Yeah.
Well, the one that we have to find on our own, where it says summarize the return period for storm depth. So
Okay, so what you're going to be doing is you're only going to have the 24-hour data. So you're going to have this row, right? So for the 2, 5, 10, 25, but you don't have 12-hour data or 2-day data. You have the 24-hour data. And I say that you should express it in terms of, let's see, do I say depth or intensity? Depth, storm depth. And so you're going to do it as a depth rather than as an intensity. Without all that other stuff? You don't. Is there a way to not show it? Oh, just the... So you excluded the range? See, what that range is referring to is a confidence interval.
Yeah, it says estimate for this table, and I just left another confidence in it, and
You left it on which? I see. So rather than copying it, you just opened a CSV and it was there. I'd never noticed that before. That makes it easy, right?
Yeah.
Okay.
You can try to copy it, and once you put it all straight down, and then
That's right. Well, there's a way of bringing it in, but still it has these bracketed ranges, and I've previously gone through and deleted each one of those bracketed ranges individually. This is actually a much nicer approach. So I'm glad you found that. I learned something new today. Now the data is always being gathered. Even though we have this statistical analysis that's been done on old data, every 10 or 15 years they update their estimates based on the fact that we're always gathering more rainfall data. And so they did that a few years ago, and here is a comparison between what we're using now. It's called NOAA Atlas 14. That's the current model of how much rainfall there is as our design storms. And the old one was called TP40. And so someone did a comparison to find out, where was our old data underestimating how much it rains, and where was the old data overestimating how much it used to rain. And so what this is showing is that in West Virginia, it actually rains less than we previously estimated based on the old data. So where it's red here, that means that the newly updated data is a little bit lower than the previous estimates. So maybe we were over-designing if we use TP40. But then Northeast Ohio, Chicago, for example, they actually had to increase their design storms for those areas because as they looked at gathering more data, it turned out to be raining more than they had previously expected. Here's a look at how many sites there are that are gathering daily rainfall totals. These are the sites that went into NOAA 14. And there's not very many stations that are gathering hourly data. If you look at this, the coverage is very sparse. There's only, maybe 20 in the state of West Virginia where we have hourly data being gathered. And the data doesn't go very far. Here's a graph of the availability and how many sites. And so for the entire eastern United States, there is only 10 sites where they've got hourly data that goes 50 years. And that's because before 50 years ago, there weren't computers to gather the data. So it was so much harder. They had to send someone out there with the ruler every hour to find out how much it rained in the last hour. And so that was very tedious. Before 50 years ago, they didn't bother to calculate, to gather the hourly data. But you need to have hourly data in order to generate a IDF curve. Yeah?
There was an article on the Weather Channel this summer, I remember, they got 95 young guys checking the weather every day.
Really?
And he had it all along in his house.
Yeah. There's actually a website that has not only NOAA rain gauges, but also like these community gathered rain gauges. And some guys are reliable enough that they actually get their data incorporated into the official estimates. But some people, it's like a hobby. You know, they gather the rainfall data and post it online. Everybody's got to have a hobby, I guess. Some people it's model trains, other people it's warcraft, and some people it's measuring rainfall. So, all right, so this. Is this an amount or an intensity? Pop quiz. Is this an amount table or an intensity table? How do you know it's amount and not intensity? Okay, so as you go down, it goes up. Well, that would be true whether it is an amount or an intensity, because both amounts and intensities are always going to have increasing quantities for bigger return periods, right? So the clue is not, it's not as you go down the table. Okay, so as you move to the right, what? It increases, and so how does that tell you that it's an amount versus an intensity? Okay, that's right. But if this was an intensity, this is an amount table. This is depth. If it was an intensity table, what should it look like? It would be kind of like the reverse of it. You'd expect the big numbers for the short storm and small numbers, small intensity for the long storm. So this is a depth table. You don't even need to have the units, although Levi mentioned you can tell because it says inches. If it said inches per hour, that's an intensity. I should block that out. So next year the quiz is even harder. Now they're not going to know. All right? So even if you don't know the units, you still should be able to like logically think through and see, okay, this has increasing amounts as the duration goes up. That means this is a depth rather than an intensity. Okay? So why does it rain more on that part of West Virginia? That's where the mountains are. That's the higher elevation. So rainfall is formed when moisture cools off. Cooler air causes the rainfall. And when there is a cooling, then there's less moisture can be held by the air. The solubility of water in air goes up with increasing temperature, and so therefore when the air cools, moisture that used to be dissolved in the air has to now come out of solution. It goes from the vapor phase to the liquid phase. And so it begins to accumulate onto a nuclei. It condenses onto a nuclei. Droplets begin to grow. As nuclei bump into each other, the drops will get bigger and bigger, and eventually they're so large that they can't be suspended by the moving air molecules anymore, and they start to fall down through the atmosphere. So this is showing that as air rises, it cools. So anything that pushes air upwards is going to have the air cool off. And then, as I just mentioned, cooling air has this process of dissolved moisture has to come out of the vapor phase and go into the liquid phase. And so there are three main things that cause air to move up: convergence, orography, and convection. A converging storm is when two air masses, one with a high pressure and one with a low pressure, run into each other, and it's called extratropical cyclonic convergence. And that sounds really like a pretty complicated phrase for it, but extratropical just means it's outside of the tropics. You know, here in North America, we're not in the tropics, so this is an extratropical region. And cyclonic means that the storm is moving in circles, which is what it does when there are two different fronts that have one a low pressure and one a high pressure. When you have cold air, which is dense, and warm air, which is less dense, moving past each other, then there happens to be some friction at the front, and that will grow, and a wave will form until eventually there is cold air and warm air, which rises, is going to be going on top of the cold air, which is more dense. And so if we look at a side view of this, what it shows is that you'll end up having warm air pushed up above cool air. And the warm air, as it rises, it inevitably is forced to cool off, and the warm air was very moist. And so you have a bunch of warm air that's moist forced up into the atmosphere, and then when it is forced upward, it cools off. As it cools, the moisture comes out of the air, and it starts to form onto the little droplets, and then rain results. So it's lifting that causes precipitation. Moisture movement and air lifting. As air rises through the atmosphere, it cools off, and it's cooling that causes the evaporated moisture to start to form little droplets. So here's another illustration of extratropical cyclonic precipitation. So you have a cold, wet front, a cold front pushing warm air up into the atmosphere, and then it cools off and causes precipitation. Okay, we're out of time, and so for the purposes of the exam, we're only going to get as far as convergence. Orography and convection won't be on the exam. We'll talk about that next Thursday, but you do need to find the section of the book that talks about extratropical cyclonic convergence, in other words, convergence, and how that causes storm, because that will be on the exam we have next Tuesday. So let's just take one final look at the announcements before you go, to remind us that your homework assignment is due on Tuesday, and we'll have the exam in class. And have a great weekend. I'll see you Tuesday. Yes, bring your computer. Always good advice.